going to talk about free fall. And to really understand free fall, you need to have a very solid understanding of what acceleration is. Acceleration is a change in motion. And when we talk about a change in motion, you know you're accelerating because acceleration is something you can feel. For instance, when you're driving down the road at, say, 70 miles per hour, how often have you looked at the speedometer and gone, oh my gosh, I'm going 70 miles per hour? It doesn't feel like you're going 70 miles per hour. But if you slam on the brakes, or if you slam on the accelerator, if you make a sudden turn, those are all things that you feel. You feel that change in motion. If you're flying in an airplane's going, what, 300-400 miles an hour? You don't feel like you're moving 300-400 miles an hour. But if there's some turbulence, that turbulence is causing change in your motion, and you feel that change in motion. When you're driving, just pay attention to that and really get a grasp of what that acceleration is telling you, because it's telling you your motion is changing. Something is occurring to change your velocity. Okay, so with free fall, we talk about a very special acceleration. It's an acceleration that's due to the force of gravity. On Earth, that's 9.8 meters per second squared, or about 10 meters per second squared. And remember, we're going to a lot of times use 10 meters per second squared when we talk about it. In your calculations, you're free to use 9.8 or 10. What the 9.8 meters per second squared or the 10 meters per second squared, what that means is that every second you're falling, like if I take an object or a book or a ball or something and I hold it out and I drop it, at the end of the first second it will be going about 10 meters per second. At the end of the second it will be going about 20 meters per second. So we could say that each second an object falls, it's falling faster by 10 meters per second. Now, in a coordinate system where the upward motion is positive, because that's the one I personally like to use, is up is positive, down is negative. So the acceleration due to gravity would always be in the down direction. So we would actually say a negative 9.8 meters per second squared, or a negative 10 meters per second squared. So here we have a lady on a cliff, and she's dropping a rock. Now, it says if a rock was dropped from a cliff in the absence of air resistance, it would respond only to gravity. We would then say that it is in free fall, and that's actually the definition of free fall. It's under the influence of one force, that force being the force due to gravity. If it's under that influence of the force due to gravity, then we would say that it is falling at a rate of a negative 10 meters per second squared. So if these were seconds, so let's say from here to here would be 1 second, 2 seconds, this is the third second, the fourth second, and finally the fifth second. So at the end of the first second, we would be going 10 meters per second. At the end of the second, 20 meters per second. 30 meters per second, 40 meters per second, and finally 50 meters per second. There's something else that you really need to pay attention to, and it's the amount of distance that gets covered each second the object is in free fall. Now, it's accelerating, so that means that its velocity is changing, and it's changing at the constant rate of a negative 10 meters per second squared. So this distance compared to that, it's going faster. If it's going faster every second it falls, then that means it's covering more distance every second it falls. And we're going to learn some formulas where we'll be able to calculate that distance. So just to kind of wrap up, I put this on the last slide. If the rock falls for 1 second, at the end of the first second, it is traveling at 10 meters per second. At the end of the second, it's 20 meters per second. At the end of the fifth second, it's 50 meters per second. If it falls for 20 seconds, it would be 20 times 10, it would be going 200 meters per second. This brings up a good point. We live in what's called, I affectionately like to call it our physics world. And our physics world, especially when we're first learning about physics, we get to take out a lot of the things that are going to overcomplicate what it is that we're learning. We need to learn the basics so that once we learn the basics, we can add in the other factors. So in our physics world, we're living in a world without air resistance. What we've done is we've taken all the particles, all the air molecules and all of that, and we've kind of sucked them out of the air so that when the rock falls, it's falling through emptiness. There's nothing to push up on it to counteract the acceleration due to gravity. Now, sometimes we don't just drop things. Sometimes we throw them into the air. If you're playing baseball or something, you throw the ball in the air. So if we take a ball, and right now we're going to look at throwing the ball straight up and straight down. If the ball is thrown straight up, during the upward part of the motion, the object is going to slow down from whatever its initial velocity is to 0. So at the very top, right up here, our velocity is 0 meters per second. It has to be 0 because you're going to stop and change direction. It then begins to accelerate just as if it had been dropped. So let's say that we are Superman and we throw the ball into the air with 40 meters per second initial velocity. And each one of these pictures represents a second in time. So if I throw this into the air at 40 meters per second, the end of the first second it's going 30 meters per second. At the end of the second second it's going 20 meters per second. So it's slowing down by the same rate that it was speeding up if we just dropped it. At the end of the next second, 10 meters per second, and then 0. Then it's going to begin to fall. Now as it falls, our direction is down. So if our direction is down, that means it's negative. Okay, and we're going to say up is positive. So on the downside, we would have a negative 10 meters per second, a negative 20 meters per second, 30 meters per second, and finally we would catch it at a negative 40 meters per second. This will trip you up. Every student has a difficult time with this in the beginning. By the end of the year, you'll rattle this off like it was nothing. But to begin with, we want to talk about this top point. At this top point, questions are very often asked on the test. What is the velocity at the very highest point the ball is going to reach? And then what is this acceleration at the very highest point that it will reach? Well, the very highest point, that's when it stops and turns around. So its velocity is 0. Its acceleration is a negative 10 meters per second squared. What's its acceleration on the way up? On the way up, all through here, its acceleration is a negative 10 meters per second squared. What about on the way down? Well, on the way down, it's still a negative 10 meters per second squared. So the thing that remains constant for this ball as it travels up, slows down, stops, speeds up on the way down. What remains constant is the rate of acceleration. The rate of acceleration is calculating how quickly the velocity changes. The velocity is not constant. The velocity is changing due to that rate of, or at that rate of acceleration. We need to begin to make the distinction between what is velocity and what is acceleration. Acceleration is a change in velocity. If you have a constant acceleration, that's telling you that your velocity is changing. Now, does how far equal how fast? Well, if you drop a ball from a cliff, what's its initial velocity? Well, if you drop it, its initial velocity is 0 meters per second. That's its initial velocity. At the end of the first second, what's its velocity? Well, we just learned that at the end of the first second, its initial velocity is 10 meters per second. Now, what you've done is you've taken 2 points in time. You've taken the point in time where you were holding it the instant you let go, and then you're also taking a point in time at 1 second. Both of those, the 0 meters per second and the 10 meters per second, are instantaneous velocities. They are the velocity that the object is going at that instant. Now, if you want to find the average, if you want to find the average of anything, what do? You take your numbers, like if you have 4 grades, you want to average up. You take all 4 grades, you add them up, and you divide by 4, and that's your average. So what we're going to do is we have 2 points. We're looking at the instant that we let go and 1 second later. And what we're going to do is take the average velocity during that second. So we're going to look between 0 meters per second and 10 meters per second. In order to do this, we're going to take this, we're going to add them together. You take 0 plus 10 and divide that by 2. Well, 0 plus 10 is 10, divide that by 2, and that is 5 meters per second. Okay, 5 meters every second. The average velocity for that first second of free fall is 5 meters per second. So you got to think about this. If this thing is accelerating, that means that its velocity is constantly changing at that rate of acceleration. So that means that it starts at 0 meters per second, and it's not until the very end of the first second that it's actually reached 10 meters per second. So during that first second, it's going from 0 meters per second, increasing until it gets to 10 meters per second. So you have to take the average of that. The average of that is 5 meters per second during that first second. So during that first second, how far did it fall? 5 meters every second. So during the first second, it fell 5 meters. So that tells us that no, how fast does not equal how far. Again, to recap, we're going to find the average. We add 2 points, all right, 2 instantaneous velocities, and we divide by 2. 0 meters per second plus 10 meters per second, divide that by 2, that gives us 5 meters per second. So, during that first second, the object traveled 5 meters and ended, we should say, so during the first second, the object traveled 5 meters and ended with a velocity of 10 meters per second at the end of that first second.